First of all, let me introduce Harry. Some of you here might know Harry. I think some of you may have advised Harry. Harry Lisabeth, he's a postdoc currently at the Energy Science. Let me get my words straight here. The Energy Geosciences Division at the Lawrence Berkeley National Lab. Harry is an alum of University of Maryland. He worked with our very own Wenlu Zhu for his PhD and graduated back in 2016. He went on to take a postdoc at the Stanford University, and now he's now at his current position at the Energy Geosciences Division. He's very interested in the interaction between chemistry and materials under stress, so things that are under pressure and under the ground, and he likes to use different kinds of experimental tools in the laboratory to characterize those material pressures or material behaviors under the conditions relevant to inside of the Earth, and hopefully we can get him to be interested in doing conditions relevant to the moon. And so he's looked at processes ranging from geological carbon storage, unconventional reservoir geophysics, and earthquake physics. And many of these, as you'll see, are actually probably very relevant to the kinds of places that we'd be looking for resources using geophysical tools. So I'd like to welcome Harry to this GEODES meeting, and he can give us an overview of his research and tell us about some of the things he's been up to. I think that will be pretty fascinating to hear. So Harry, take it away.
All right. Thanks, Nick. Let me share my screen here. All right. All right. Can you guys see these slides?
Yes, that's great.
All right. Great. So I'm going to be talking a little bit about the acoustic properties of materials at low effective stress. And that's going to involve talking a little bit about an interesting sort of literature history in studying the acoustic behavior of ultra dry rocks that's motivated by some of the early lunar seismology. And then I'll talk about some sort of more recent advances in indoor geophysics, studying some more ways that we may be able to tease out trace amounts of volatiles in these rocks and some other things that could be relevant to future exploration of the moon. So, you know, there's definitely volatiles on the moon. You guys know better than me. There was just a big press conference. There's more volatiles than we thought on the moon. They're all over the place. Once we're up there, how do we find them? How do we map their distribution? How do we learn some more things about them? Obviously, there's a range of geophysical techniques that we could use, GPR, electromagnetism, but are there ways that we can use seismic observations to map the distribution? And I think that actually on Earth, rock physics is dominated by pressure and multi-phase fluid saturation effects. This is a field that's been very widely studied for various technical applications, but up in outer space, in light vacuum or high vacuum, we have low stress conditions and we have extremely dry conditions. And under those conditions, there are sort of different sensitivities to the acoustic behaviors of the materials. And I think that actually is a benefit for us if we're trying to look at the role of volatiles on the moon. And in particular, there are three quantities that we can use seismic observations to pick out, and that's attenuation, velocity, and nonlinearity. And those are all things that have feedbacks to trace volatiles, and I'll talk a little bit more about that, and then talk a little bit about the ways that we can calibrate these things in the lab for potential future experiments on the moon. So attenuation, that's the first one. And this starts with a sort of interesting history of lunar seismology that they noticed when they were doing some sort of controlled thumper experiments up on the moon, that the absorption of seismic waves was extremely low relative to what has been seen on the Earth. So these are some thumper shots that, also, I guess there's some natural events here, and the landing of one of the lunar modules. But it was observed that the moon essentially rings like a bell. the duration of some of these events was like 4 hours. And then on the bottom here, there's an explosive test from White Sands that is extremely truncated compared to these other histories, but just showcasing that on the Earth, seismic energy is attenuated much, much faster than what was observed on the moon, which is somewhat surprising given that the outer layer of the moon is essentially a bunch of dust that's been sitting around. There was continued investigation into this, into taking a closer look to try to quantify, okay, what's the Q of the moon? And they were getting numbers that were up around 3,000-4,000. The continued investigations found numbers up to 4,000 and even QS up to 7,000, analyzing different amounts of data. So just to give you a general idea of typical values of Q on Earth, for granular materials, which is probably similar to what the regolith is, Q is on the order of 10, 15. In sedimentary rocks, 30, 60, crystalline rocks, 200, maybe 600, when you have something that's under extremely high pressure, really low porosity. And so the moon rocks are, at least an order of magnitude, but maybe 2 orders of magnitude if you're comparing it to granular of material, higher than anything observed on the Earth. So it was a little bit of a conundrum. People had a number of different ideas about why this might be so, but there's a sort of parallel line of studying the properties of the materials brought back. And this is someone who, just did sort of a really basic study of taking a look at some lunar dust and doing some etching to look at the sort of microstructures of the material from the regolith. And they were working on some rocks that had been contaminated. They had been, basically the vacuum that they had been stored in had been released, and they were looking at the material. It was all sorts of interesting observations, but nothing particularly unique until they put them back under ultra high vacuum to put them more into the state that they were up on the moon. And they found some interesting properties, including a time-dependent adhesion and interesting interaction of electrostatic charge. So basically, they put these things under ultra high vacuum, and they noticed that the little crystals stuck to one another and stood up straight. And after some amount of time, they would kind of fall over. And this suggested that the sort of attractive cohesive forces between the grains was augmented in ultra high vacuum. Meanwhile, this guy, Bernie Tittman, was doing some interesting rock physics experiments, doing bar resonance experiments to measure the Q on some material from the moon and also various analog materials. And the analog materials, the materials from the moon, showed like terrestrial values of Q around 60 when in humidity. But when basically baked off and put in ultra high vacuum in order to drive off trace amounts of water, he was able to recover values of Q that were similar to those that were actually measured on the moon, up to 3,000, suggesting that thin layers of adsorbed water were responsible for this dramatic decrease in Q when materials are found in ambient humidity. He then went on to do a number of sort of exhaustive studies of this phenomenon to try to understand what's going on, and studied the vapor pressure dependence of Q in the materials, and found that, in fact, at very low Q, that at very low partial pressures of water, you have high Q, and then that sort of reduces as you increase the partial pressure of humidity. But he went on to study the effects of other chemicals. So here we have QS versus partial pressure, and this is water in the squares and benzene in the circles. And as you can see, water shows this sort of dramatic drop off quickly, and then it sort of flattens out. Whereas benzene, which is a non-polar molecule, doesn't have this same effect. and doesn't start to show a dramatic reduction in Q until much higher partial pressures. And that was interpreted to have to do with basically the adhesive behavior of the molecule on the surface, that being a polar molecule, water adsorbs strongly at first, and then there is at very high partial pressures another drop off of Q that indicates some sort of capillary condensation of the water. But for the benzene, you get very little absorption effects, and you only get an effect once you start to have capillary condensation of the fluid. But it's not just polar or nonpolar, it also has to do with specifics of the chemistry of the molecule. So here is the quality factor versus partial pressure for water and methanol. And you can see that there's slightly different behavior, which has been attributed essentially to the dipole moment of the molecules, again, having to do with the dynamics of adsorption of the molecule to the surface of the materials. So now I'm going to move on to the second quantity, which is velocity. Velocity is related to the material properties of the rocks through a modulus or a stiffness and the density. Using Hertz-Mindlin contact theory, which is a theoretical framework for studying the contact behavior of different particles, you can look at the normal and shear stiffness of contacts as a function of the contact area and the material properties. Now, for a given geometry, you can map the contact area for just two physically contacting spheres. But later work has gone on to study how these contacts evolve, both under application of normal force, but also modification of surface energy, which modifies the electrostatic forces that are drawing these two theoretical spheres together. So this is sort of getting at what that original Grossman paper was observing, that there's a cohesive force between these particles that is particularly operative when things are super dry. But the adsorption of molecules is going to modify the surface energy of the whatever materials that it is you have, and it's going to modify the cohesiveness. And so you can use this sort of model to look at the behavior of contacts at really low effective stresses. So this is a stiffness versus normal load curve. And it shows that at extremely low stresses, low effective stress, the stiffness is dominated by these cohesive forces. And the cohesive forces are modulated by the surface chemistry. So because stiffness is related to acoustic velocity, you can tease out information about that cohesion by using the sort of systematic behavior of the acoustic velocity. And so you can basically make some predictions about changes in stiffness as a function of partial pressure for various different molecules. And so water, as you can see, has a particularly strong effect. Benzene is predicted to have a smaller effect. And here, comparing the theory to some actual data, which are shown by these points, it does an okay job. Not perfect, but showcases the general behavior of how the modulus changes as a function of partial pressure. So this is all just assuming like a normal kind of linear elasticity, although, as you can see, at really low stresses, the elastic behavior is in fact nonlinear. But there are other mechanisms that lead to nonlinear elasticity. And nonlinear elasticity basically means there isn't just one coefficient of proportionality between stress and strain, but in fact, there are a number of other parameters. Here, they're parameterized as beta, delta, alpha, and they show the strain and strain rate dependence of elastic behavior. So in particular, of importance here to studying fluids within rocks is this parameter alpha, which is the parameter that is used to showcase the strength of hysteretic nonlinearity, which is common of the behavior of fluids in a porous material. So linear elasticity, this is something we're all familiar with. The modulus is constant. Stress strain curves have a constant slope. First order nonlinearity, this is that beta term right there is sort of showing that the modulus softens and stiffens with strain, leading to sort of curved stress strain curves. Second order means that the modulus softens sort of in either direction, leading to the sort of S-shaped stress strain curves. And hysteretic nonlinearity just has the modulus dependent on history, and then you get these sort of stress strain loops. And that is typical of water, because if you perturb the state of a material that has some fluid that's within it, then that state is going to be different, and that's going to lead to this sort of hysteretic behavior. One way that you can sort of characterize this is by looking at a frequency shift in a resonant experiment. So this is an example of some data from a resonating sandstone sample that essentially has a given characteristic resonance frequency, and the shift of the resonance frequency as you increase strain is proportional to that alpha, the hysteretic nonlinearity coefficient. So if you had a totally linear material, for instance, if this was a bar of aluminum or something like that, that had no damage in it, then as you increase strain, you would just basically increase the amplitude of this peak, but not shift the frequency. And the shift in frequency is indicative of this sort of hysteretic nonlinear behavior. And you can see that hysteretic nonlinearity, indeed, as well, is sensitive to fluids within the material. So this is an example of two sandstones that have, going from partial all the way to full saturation. You can see that particularly at low saturations, you have dramatic increases in hysteretic nonlinearity. And what that means is that, this parameter, hysteretic nonlinearity, is a really sensitive indicator of the presence or absence of fluids, particularly when there is a sort of small amount around. Another interesting aspect of nonlinear elasticity is a phenomenon that's called slow dynamics. And what this is essentially a hysteresis of hysteresis. That hysteretic behavior is sensitive to perturbation. So once you look at sort of the increases in hysteresis at large strain, then when you go back to smaller strain, there's some memory of the large hysteresis from the large perturbation, and it's fully recoverable and showcases a sort of log T recovery from the perturbation of that state. And so slow dynamics is usually defined as some sort of transient evolution of elastic properties after some sort of perturbation. So this is a good example of, this is a sort of resonant spectral peak before perturbation is then perturbed, basically shaken pretty hard, and then that hard shake is brought back to the lower level, and you can see that there's a perturbation from the initial value, and then there's a log T recovery afterwards. And this particular experiment was actually done in an ESEM, which means that they could watch what was going on during this perturbation. And so it was a porous silica sample. Here's a pore under high vacuum, and then here's a pore at, I believe it was 30% ambient humidity. You can see that there's capillary condensation of fluid within the sample. And then once the sample is perturbed, the fluid kind of disappears, and you can watch during the recovery phase as the fluid sort of recondenses here. So this is another possible way to sort of probe the presence and behavior of fluids in a porous material. Okay, so how do we take a look and measure some of these properties in the lab? I'm going to show an example of some characterization of a fractured dolomite sample. So this is a sample that's taken from a well from northern Montana, and we cored through a natural fracture so that we could measure the sort of elastic behavior of this single natural fracture itself. Characterize the sample, you can scan it with CT to take a look at the aperture. You can use profilometry to look at the roughness of the sample. And this sample in particular showcases a little bit of a fabric. It's got a kind of lineation that I've indicated by this, this direction here. And if you take a profile normal to the lineation versus parallel to the lineation, you can see that there's a systematic difference in roughness, which will be relevant in interpreting the data later. Other ways that we can characterize the fracture surface is using pressure sensitive film. So this can both map the change in size and shape of the asperities, but also the localized pressure on each of the asperities. So this is a sample that has the film in between the fracture, and it's loaded uniaxially to various different stress states. And then we can look at the evolution of the contacts under the different stress states. And then you can look at different statistics about the asperities as you're increasing in pressure. As you can see, the number of asperities increases the most at low pressures, and then less as you're increasing the pressure, and the contact areas is sort of quasi-linear. Another great way to characterize these fractures is using X-ray tomography. We have capabilities to do in situ X-ray tomography at Berkeley Lab. So we take a pressure vessel that has the possibility to apply both a confining pressure and an axial pressure, and you can put samples in there. So I put a sample of this natural fracture in there to measure it at different stress states, and you can watch asperities form and deform. And ultimately, you get a really high resolution view of what the fracture looks like. And so you can use this to look at fracture roughness, fracture aperture, and these sort of windows through the data here are the asperities. And you can also use this method as another way to look at changes in asperity geometry, and use it to make aperture maps as a function of pressure. So as you can see, at low pressure, there's sort of a wider spread of different, or a smoother spread of different apertures. As you increase the pressure, you tend to close the places with small aperture, but there are the areas with the largest aperture persist. So as you're increasing in pressure, you sort of emphasize whatever those high aperture frequent features are, because you've closed the smaller, the thinner areas. And the typical way in the lab that we characterize the acoustic behavior of materials is using ultrasonics. So I took this sample of dolomite and put it in a pressure vessel with plumbed with some high pressure flow throughs and some ultrasonic sensors in order to measure the acoustic behavior at a variety of conditions. So I took the samples from essentially 0 to 20 MPa with a constant pore pressure of 10 MPa, using a P and 2 S-wave transducers, making measurements with air and brine and CO2. And this allows for the calculation of the effective pressure and fluid replacement effects of the acoustic velocity. So this is what the data looks like. So you can see this is a P wave. The darker curves are higher pressure. The lighter curves are lower pressure. So you can see that at higher pressure, you have earlier arrival times and higher amplitudes. You can look at this in the frequency domain as well and see that, again, at higher pressures, you have higher amplitudes and generally higher frequencies, higher central frequencies of the transmitted energy. You can use this to calculate the changes in velocity and the changes in attenuation in the sample. And you can see that, we get these sort of typical curves where you have an increase in velocity as you increase pressure. but of particular interest is this really low effective stress regime. And that is where you have the greatest sensitivity to changes in pressure, because you have a dramatic increase in the velocity at lower pressures, and that sort of like evens out. And if you were to look at a curve like this for a solid sample, I probably should have plotted one, but you have the same shape, but this feature, this extremely low pressure feature, isn't there. You still have a an increase in velocity with an increase in pressure, but because the rock is intact, it's more cohesive, and so you don't have this feature at the very lowest effective pressure. And that has to do with basically the loss of cohesion and the dynamics of the evolution of the asperities at those very low pressures. And that's something that'll be really important to get a better understanding of, for understanding the acoustic behavior of, for instance, the regolith. You can see the same thing in the attenuation. So here I have plotted Q, which is the inverse of attenuation, but you can see that at very low pressures, again, we have the greatest change in attenuation, and it's particularly pronounced for the sample saturated with air and CO2. But you can still see the same thing with the sample saturated with brine. QS shows the same behavior, but in fact, below 5 MPa confining pressure, I didn't have the signal to noise to actually do a reliable calculation of QS, but that in itself attests to the fact that the Q is dramatically lower at those pressures. So because we have two orthogonal shear waves, that allows us to look at shear anisotropy. You can see that as the pressure increases, the velocity anisotropy decreases, but as the pressure increases, the attenuation anisotropy increases. And that's kind of an interesting observation, because typically velocity and Q are positively correlated. So it's interesting that the anisotropy would show this different trend. And the reason that is because it's giving us information about different aspects of the system. So using that, the data from the pressure sensitive film experiment, I can calculate a mean asperity eccentricity as a function of pressure. And you can see that qualitatively you get the sort of same behavior. This reduction in shear anisotropy correlates with a reduction in asperity eccentricity, basically confirming that the velocity is telling us about the sort of character of the contacts within that fracture. And using the tomography data, I can run permeability experiments in order to compare the attenuation anisotropy with permeability anisotropy. And again, we get a good correlation, because as I was showing in the sort of aperture maps, at higher pressures, because you have these persistent high aperture features, at higher pressures, basically the flow channels and the geometry thereof are emphasized. And anisotropy or attenuation is often related to hydrodynamic phenomena, because it's a bunch of molecules moving around dissipating energy. So another unique capability we have at Berkeley Lab is the ability to do really low frequency, really seismic frequency and below measurements of these samples. And we use this apparatus, which is essentially a torsional spring with a sample in the middle. It's free on one end and driven by magnetic drivers and stiff on the other end. And we drive the magnetic drivers in torsion, and then can measure the twist on the free arm and the torque on the stiff arm, and convert that to stress and strain. And so we can measure the shear modulus and attenuation of the sample at these extremely low frequencies. And this actually also has the ability to apply a uniaxial stress, so you can do fractured samples and look at the pressure dependence of these properties as well. This is what the data looks like. You apply a sinusoidal oscillation, and then you use the stress and the strain to if you plot stress versus strain, it kind of looks like this nice little ellipse right here, and the slope of the ellipse is your modulus, and the area inside it is your attenuation, or the phase lag between these two signs. We can use this to look at the really low frequency modulus and attenuation. Again, this is an intact dolomite sample, same material as from the ultrasonic study. And you can see that for the intact sample, the shear modulus and attenuation are fairly constant. I still have yet to do the measurements on the fractured sample, but those will be interesting results. But what we can look at is at the normal stress dependence. So these are all measurements taken at 1 Hertz frequency with different normal stress on a fractured dolomite sample. And you can see that for an intact dolomite sample, you have a small pressure dependence of the modulus, but it's pretty much constant across the sort of 0 to 10 MPa range. But for a fractured sample, not only is the modulus generally lower, but you have a much stronger pressure dependence, particularly at very low effective stress. You can observe the same thing in the attenuation of the sample, that the attenuation at in an intact sample is relatively constant over this stress range, but you have elevated attenuation at in the fractured sample at low normal stresses. So we can compare this to the data from the ultrasonic study. So this is comparing, data from 1 Hertz to data from 1 megahertz. And this indicates that the sort of qualitative relationship is the same, that you have, less pressure dependence in an intact sample and generally higher shear modulus, and generally lower shear modulus and higher pressure dependence in a fractured sample. But generally at higher frequencies, the sample is stiffer, and this indicates that there's some dispersion in the material, which is pretty typical of most earth materials. Same observations hold for the attenuation in the sample. You can see that attenuation is much higher at megahertz frequencies, and that's because in addition to a number of dissipation mechanisms at low frequency, there's significant scattering at the megahertz frequency range because the wavelength is comparable to the elastic structure of the rock itself. But you have the same systematic behavior, that the intact sample shows less pressure dependence, although the intact sample at really high frequencies shows some pressure dependence at the lower frequencies, and that's because there are microfractures, grain boundaries, things like that in the rock, and the high frequency energy is sensitive to the closure of those, whereas the really low frequency measurement is not, leading to the constant attenuation. Another interesting thing about this this low frequency apparatus is that you can use it to do some of these nonlinear characterizations, and you do that by applying either looking at harmonic generation as a result of the nonlinearity. So if you have these, basically, if you apply a sinusoidal variation to stress or strain in a sample exhibiting any of these nonlinear behaviors, you'll get a distorted signal. And that, if you look at that in the frequency domain, results in the generation of harmonic frequencies. You can also leverage this interesting property by doing a nonlinear wave mixing experiment. So if you excite the frequency not at just one frequency, excite the sample at not just one frequency, but two, then you can look at how those frequencies mix. In a linear material, you put in 2 frequencies, you get out 2 frequencies. In a nonlinear material, you put in 2 frequencies, you get out both the fundamental frequencies and sum and difference frequencies of the 2 input signals. And so what that looks like is sort of sideband energy in the frequency domain. And you can use the systematic change of sideband energy as a function of different conditions to look at how those conditions are affecting the nonlinear behavior. Nonlinearity also manifests as a distortion of the stress-strain ellipses and leads to this sort of cusping behavior. So you get pointy ends that can be sort of tilted up and down. And in the frequency domain, those cusps are the thing that lead to the harmonic generation. But here's some interesting data from one of these wave modulation experiments. So this sample was excited at both 1 hertz and 100 millihertz. And then we're looking at the data in the frequency domain. The black curve is an aluminum sample, so you can see that you pretty much just get the fundamental frequencies. For an intact granite sample in blue, you get pretty much the same behavior, maybe a little bit of harmonic generation that's starting. But when you put a fractured granite sample, so this is a granite sample with specifically an induced tensile fracture in the middle of it, at high normal pressure, so 10 MPa closing that tensile fracture, you still get the generation of these sidebands and also the generation of some harmonics. And at low effective pressure, so that tensile fracture is somewhat open, you get substantially higher sidebands. You see this is a log scale, so there's a pretty dramatic increase in the amount of sideband energy that you get. And you also get the generation of more harmonics and even some harmonics of the sidebands themselves. And so you can use sort of the harmonic amplitudes as a function of strain, here as a function of drive voltage, which is you know, a sort of a proxy for strain, and see that you get different signals for different basically structures of damage within the material. For the single tensile fractured granite at low drive voltages, low strain, you don't get significant nonlinear behavior, and you reach some threshold where it starts to increase. And for a thermally cracked granite, so that means that you have sort of distributed tiny microcracks all through it, cracked grain boundaries, you start to get nonlinear behavior at much lower strains. This is just some sort of initial characterization to show the sort of studies that can be done to look at the unique or non-unique signatures of various things. This is using damage as the cause of the nonlinearity, but studying the effects of volatiles in the material, studying how adsorption to these fracture surfaces affects this nonlinear signal, I think is an interesting avenue to explore because it's so extremely sensitive and may be able to find really small amounts of volatiles interacting. So just some quick conclusions. The changes in velocity, attenuation, and nonlinearity are particularly pronounced at low effective stress, which is positive for looking at the lunar regolith. Pressure-induced changes in velocity, and particularly attenuation, are more pronounced at seismic frequencies than ultrasonic frequencies. So that is something to consider for designing experiments. And advances in our characterization of the effect of volatiles on attenuation and nonlinearity could lead to some well-constrained rock physics models for the calibration of future lunar experiments. And I'd like to thank some of my collaborators who helped with all of this stuff. And I'd be happy to take some questions. I'm particularly interested to sort of talk through some ideas for future studies that could be helpful to the kind of characterization you guys are hoping to do.
Thanks, Harry. That was great. I assume there's some questions out there, so you can just unmute yourself and ask your question, or if you have a question and you just want to type it into the chat, feel free to.
This is Danielle, if I can jump in. This was all excellent work. I was like geeking hard, so I liked this talk. I think one of the things that I didn't really see in all of this work, and maybe it's because you haven't gotten there yet, is I do mostly physical experiments rather than numerical. And what we have found is a lot of stick-slip behavior. So you don't have like that one failure event. You have like these kind of short staggered steps of a small failure and then a major fail. And I was just curious as to your thoughts on that.
Yeah, well, so I guess one of the things that I should have mentioned is that these most of these experiments are done at really low strain levels, and because I'm talking here about elastic or quasi-elastic things, there's actually no failure that's going on. So the deformation that's happening is recoverable. So the dynamics of some of the nonlinear behavior probably have to do with microscale frictional failure of sort of the less stuck annulus at the outside of asperities. But because there's a restoring force from the stuck center of it, even though there's some failure, it's called partial slip of the asperities, they snap back when the stress is reduced. So all these things that I was showing are actually really elastic recoverable things, and not in fact failure or plastic.
Okay, yeah, thank you for that clarification.
Sure.
Harrison, this is Chuck Connor. I really thought that was a cool talk, and a lot of it's new to me. So I was wondering if you could explain why the hysteresis-related nonlinearity is likely associated with fluids and not necessarily only with pore shape and permeability.
Well, I would say that the hysteretic nonlinearity is often just phenomenologically, it's a relatively new area of study. Maybe 20 or stretching back 30 years of people really, taking a close look at it. And from a lot of the experimental studies, that hysteretic nonlinearity has just been associated with relative humidity or partial saturation effects and things like that. But there are other things that lead to hysteretic nonlinearity, including frictional effects, which is another thing that's of particular interest. At very low effective stress, you're more likely to get frictional failures, or micro frictional failures and things like that. And that's another reason for looking at this sort of strain amplitude dependence of the particular phenomenon that you're looking at, because a strong amplitude dependence could be indicative of a frictional process, which is probably the case for these fractured samples. But all these experiments were done at sort of ambient humidity, and looking at humidity effects as another sort of axis on here is something that we're really interested to do, and I think will be really important.
Okay, thanks. That's cool.
Yeah.
So I have a question for you, Harry. So, we're talking about volatiles and films, right? So on the surfaces of things, when we're talking about looking at water or other kind of thing, I guess in the lunar environment, those would probably take the form of ices or other kinds of surfaces, depending upon whatever it is that you're looking at. Some things have a relatively low freezing temperature. But do you think that the presence of ice in a lattice system of fractures or whatnot would have some sort of the same kinds of effects, especially in changes in the friction and that kind of thing in the system, that might be detectable through some of these kinds of methods?
Yeah, I mean, it's a great question. I haven't seen any work in that area, but the fundamental description of sort of non-linear elasticity has to do with the complicated structure of rocks. It basically has to do with the fact that these, the micro cracks in the rock and the grain boundaries have different parameters, and averaged over a large enough medium, it leads to this sort of complex aggregate behavior. So I would imagine that having ice in those cracks is going to change it. But I would also say that, even at very, well, two things. If some of the volatiles are existing in extremely small pores within individual elements of the regolith, I think that it's possible, materials just behave differently on those tiny scales. So, if you have a single monolayer adsorbed to a fracture or a grained surface, its physical description is different than bulk water and different than ice. It sort of has a quasi-crystalline structure to begin with, even though it's not technically ice. I admit that I don't really know enough about the cryogenic surface chemistry to speculate, but I have to imagine that it's a very rich area for investigation.
Yeah.
If I can just jump in here real quick, yesterday at one of the GSA sessions, I heard to talk about the development of hoarfrost that on these very dry and low pressure environments, that a lot of these pore spaces may be filled more in crystalline fashion. So that makes me think, just follow on, a crystalline hoarfrost ice in these pore space would be compressible versus, liquid water would not. So yeah, I just wanted to throw that out there, that we don't really know a lot about the nature of these ice in these pore spaces, but it may come into play in your models down the road.
Are there any other questions for Harry? I think Derek and Joe had to leave, but they do these simulations where they shake materials essentially in low microgravity and see basically how the size fraction distribution can evolve through time through this thing where larger things tend to float up to the surface. And it strikes me as this sort of hysteresis, right? The deformation of that material would have a pretty big role in determining some of these properties, right? So just as more of a comment, one of the questions that we are addressing is essentially, how could we look inside of asteroids or other sort of low gravity bodies that may have had this history, this period of time where they've been either impacted and shaked, or just through Yorp effects or sort of gravitational instabilities in the rotation, you can actually shake and move the grains around inside of that. So you can kind of think of this asteroid as this rubble pile. So this
How do they do the experiments in microgravity?
So they're doing it simulations in computers.
Okay,
they're actually able to put in like a jar of particles of different shapes and relationships of the grain boundaries, and then essentially shake it with an applied force and see how things evolve. So it's kind of like, the theoretical rock physics approach, only now they're taking sort of a particle approach and looking at how the grains behave with one another.
Yeah, that's one of the things I've been thinking about since the last time we talked is, how do you do, how do you make any of these measurements in something approximating microgravity?
Drop towers.
Yeah.
You build it. We have a researcher doing this kind of, how do you build small bodies, right? That meter scale problem. And so we're currently in the midst of building him a new drop tower. So I would say in general, there's ways.
Interesting. Well, maybe we need to get some ultrasonic sensors into the drop tower and drop some sand columns.
I'm good with that. Let's talk.
All right.
Okay, well, we're pushing up against the hour here, and I know folks that have 2 o'clock commitments probably need to run. Well, I want to thank you, Harry. This was really interesting, and I think that there's a lot of really sort of fertile ground here for creating new collaborations and potential projects. It sounds like there's already one with Danielle.
Yeah, absolutely. I'll throw my email into the chat here. Feel free to follow up. I'd be happy to talk more about any of this stuff.
And we're going to post your talk on the GEODES website so that other team members who weren't able to be here can go back and view it. So
all right.
I'll put your contact information there so people can get in touch with you if they want to talk to you some more. So,
great.
All right. Well, thank you, Harry, and thanks everybody for sticking with it and hanging out with us for an hour talking about some geophysics and the properties of materials. Hopefully, we'll see many kinds of talks like this in the future. So, I look forward to working with everybody over the year. Have a great day, and let's adjourn.